A very good afternoon and a warm welcome to everyone in this public talk, which is about black holes and observation by Professor Jasjeet Singh Bagla, Department of Physical Science, Indian Institute of Science Education and Research, IISER, Mohali. Planetarium welcome you, sir, for accepting our invitation and agreeing to talk and share your knowledge amongst the interested ones. Professor Jasjeet Singh Bagla was born in Agra in 1969, a town in North India famous for the Taj Mahal, amongst other things. Delhi is where he grew up, went to school, college, and university. Later in 1992, he moved to the Inter-University Center for Astronomy and Astrophysics, popularly known as IUCA Pune, as a research scholar. His PhD thesis was titled Gravitational Clustering in an Expanding Universe. He joined the Institute of Astronomy in Cambridge, UK, as a postdoctoral research in 1996, where he worked for 2 years. He spent a bit more than a year at a Harvard Smithsonian Center for Astrophysics in Cambridge, MA as a postdoctoral research associate. Later, then Professor Bagla joined the Harish Chandra Research Institute HRI in Allahabad in the physics department. At present, he is working at the Indian Institute of Science, Education and Research, IISER Mohali. Beside his subject, he is also interested in photography, listening to music, reading, and watching movies. Planetarium is privileged to host you, sir, and to have more depth understanding about the topic we are discussing today. This video will be available on the Planetarium YouTube channel. So in case anybody missed today's live, can always refer as a source of information. So over to you, sir.
Thank you. Thank you so much for the kind introduction. I would like to add that in mid-1980s, just as the Amateur Astronomical Association of Delhi, AAAD, was coming up, I was a member, then secretary, and I was a regular at Nehru Planetarium. I learned most of my sky watching over there. So it's always a pleasure to connect with the Nehru Planetarium, always. All right. So the subject for today's discussion is observational evidence for black holes. And I would like to start by recalling that a large part of what I'm going to talk about was rewarded by the Nobel Prize in Physics 2020, where Roger Penrose from Oxford, he had half the share, and Reinhard Genzel from Max Planck Garking and Andrea Miages from UCLA, they had 1/4 share each. So Roger Penrose, of course, is a theorist. The other two are observers, and I will talk about their work as well as work of other people, which has led us to believe that black holes do indeed exist, even though an ironclad proof is still not something that we have with us. So let's start with Roger Penrose. He is currently Emeritus Rouse Ball Professor of Mathematics at the University of Oxford. He was born on 8th of August 1931 in Essex. He trained as a mathematician and graduated from University College London. He did his PhD from Cambridge in tensor methods in algebraic geometry. And then he went on to introduce use of topology and topology of light cones to study spacetimes. So gravity, of course, we know people knew about gravity all along, but Newton conceptualized gravitation as a universal force. This was in the 17th century, and it was successful in explaining not only terrestrial phenomena like balls falling down or stones or apples falling down, but also planetary motions. Specifically, he could explain the motion of the moon and falling objects on Earth with the same law, and that is why it was something that caught on very quickly. And once it caught on, scientists started to analyze implications of the gravitational force law that Newton had given. Discovery of Neptune in 1846, as it was predicted through very detailed calculations, was a high point amongst many successes of Newtonian theory of gravity. So to recall, Uranus had been discovered a little while earlier, and people realized that the orbit of Uranus cannot be explained unless we postulate existence of another planet in the solar system. And when people did that, they came up with a prediction of where Neptune should be and what its orbit should look like. And lo and behold, Neptune was discovered the moment astronomers looked in the direction that theorists were pointing to. So that amazed people, that you can predict existence of a planet without having ever seen it before. And that increased the amount of confidence people had in Newton's laws of gravity. Of course, it's interesting that this happened in 1846, and about 70 years down the line, Einstein was giving his general theory of relativity, which was verified in 1919 by Eddington, Dyson, and others. So Newton came up with his law of gravitation, and Ole Rømer from Denmark, almost around the same time, was the first person to measure the speed of light. He did so by observing eclipses of Io, a satellite of Jupiter. So the observable over here is that as the Earth is moving towards Jupiter in its orbit, the time between two successive eclipses of Io becomes a little bit smaller, whereas when the Earth is going away from Jupiter for the next 6 months, the time between successive eclipses of Io becomes a little bit larger. And interpreting that as a Doppler shift, one can estimate the speed of light, and that is what Rømer had done. And he got the correct order of magnitude, although not the correct value for the speed of light. I like this particular discovery a lot because redoing Rømer's experiment was my bachelor's thesis project, and I managed to get the correct order of magnitude, which I was very happy about. Extreme gravity and dark stars. So there are two people who came up with the idea of black holes, which they called as dark stars at that time. One was John Michel and the other was Laplace. So what they said was that what happens if I have an object which is so massive that its gravitational force does not let light escape? So we know the law of gravity, we know the speed of light, and we can calculate the escape velocity from any object. If the escape velocity turns out to be more than the speed of light, then it is obvious that light will not be able to escape to infinity from that object. So this is Michel's writing. If the semi-diameter of a sphere of the same density with the sun were to exceed that of the sun in the proportion of 500 to 1, a body falling from an infinite height towards it would have acquired at its surface a greater velocity than that of light. And consequently, supposing light to be attracted by the same force in proportion to its inertia with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. And then, of course, he goes on to look at kind of conjecture as to what that means. He says that if such bodies exist, then we would have no information from sight. Yet, if any other luminous bodies should appear to revolve about them, we might still perhaps be, from the motions of these revolving bodies, infer the existence of the central object. So what John Michel was talking about was possibility of what we today call black holes, and then asking how we may observe them. And he comes up with an interesting solution that if there are other objects, planets or stars in the vicinity which are going around this dark star, then from the motion of those objects, we will be able to infer that there is a massive dark object sitting over there. Laplace had similar thoughts. This is in French. And he came up with a very, very similar set of ideas, and he published them. So we have two gentlemen postulating the existence of what we today call black holes more than 200 years ago. So the escape velocity is a familiar concept. We all know that if we throw something in the air, throw it upwards, then it goes up and falls down. If I throw it at a higher speed, then it goes higher before falling down. And I can then ask what should be the speed such that the object never falls down. That is what we call the escape velocity or escape speed. And we can show that if we have an object of mass m and radius r, then the escape velocity or escape speed is 2gm by r square root. We can easily calculate the value for the Earth. What these two gentlemen did was to say that if v escape is equal to the speed of light, which is 3 lakh kilometers per second, then what would be that would be a dark object. But you can see from this formula that then for dark objects, we immediately have a relation between their mass and radius. So it remained for a very, very long time, and there was no progress in this direction for the simple reason that there was no way at that stage of making an observation. Einstein moved forward in the sense that he took the Newtonian gravity, which works with in three-dimensional space and time as an external parameter, to the notion of curved space-time. And Einstein proposed that gravity should not be treated as a force. Instead, gravitational effect modifies the space-time in the vicinity of objects. And he took the idea further in a mathematical way to come up with what we call the general theory of relativity. And of course, in this, special relativity is applicable in small regions in freely falling frames. So Einstein, of course, even though he did the calculations for general theory of relativity, he was not the one to come up with the notion of black holes. That was done by Carl Schwarzschild, and his was the first exact solution in general theory of relativity. He assumed existence of a point mass and spherical symmetry, and the situation being static in the sense there is no change with time. And he found a singular solution. Singularity is at the center, at the origin, but he showed that the origin is surrounded by something which is now called a horizon, such that nothing can escape from it. So interestingly, the relationship between mass, radius, Newton's gravitation constant, and the speed of light is exactly the same as you would get if you use Newtonian idea of escape velocity. So one comes up with the idea of an event horizon or Schwarzschild radius or radius of a black hole, which is 2gm by c square. So if I plug in the mass of the sun, we get a black hole which has a radius of about 3 kilometers. But Schwarzschild and later people also realized the existence of what is called a photon sphere, where light or photons can get into a circular orbit around the black hole, and that happens at the scale of 1.5 times the black hole radius. So for sun, you will have to compress the mass of the sun into a radius smaller than 3 kilometers, and the photon orbit will have a radius of 4.5 kilometers. So in a Schwarzschild black hole, so I'm looking at theory first, I'll come to observables and observations later. It's somewhat easier to appreciate observations once we know a little bit of theory. Nothing can escape from this event horizon, things fall in, therefore it's a one-way membrane. And as I mentioned at the last slide, photons can be in a circular orbit at a radius of 3gm by c square. The smallest or circular orbit for massive particles is at twice this radius. It is at 6gm by c square. Now, unlike Newtonian mechanics, where any particle with a non-zero angular momentum can never fall to the center, in Einstein in gravity, in general theory of relativity, even particles with a non-zero angular momentum can fall to the center, as the centrifugal barrier does not extend to infinite energy. So space-time for a star looks like some kind of a stretched net or a pit, whereas space-time for a black hole would have a cut at the bottom, so the things just fall down, and we have a singularity. So when Schwarzschild looked at the solution for a star like the sun, the solution is not singular, there is no horizon, and the solution outside the star matches with the solution for a point mass with the same mass as the star. The interior solution depends on the details of density, pressure, and how these vary with distance from the center. So all of this was happening in 1910s and a little bit of work in 1920s. Around 1930, Chandrasekhar came up with this derivation where he showed that if we have degenerate white dwarf stars, they cannot have a mass of more than 1.4 times the mass of the sun and be stable. So this is now, of course, called the Chandrasekhar mass limit. But then people started asking what happens if a white dwarf of a larger mass forms, or if a low mass white dwarf somehow gains some mass. People conjectured formation of neutron stars, but these were discovered much, much later. And the work on what can happen next was first done by Vishweshwar Dutt at the Presidency College in Kolkata, where he discovered the analytical solution for collapse of a pressureless spherical ball of dust. Unfortunately, he died in a hernia surgery in 1938. His solution was finally published as a golden oldie in 1997. Oppenheimer of the atomic bomb Los Alamos fame and Schneider, they independently discovered the same solution in 1939, that is before the start of Second World War. And they showed that this leads to formation of an event horizon and a black hole. So what they said was that if I have a pressure-free medium, which is spherically symmetric, and I let it go, then it will naturally form a black hole. So people, of course, started asking that, a star has pressure, it is not pressure-free, so will a star collapse to form a black hole or not? That is still an open question. So it was partly addressed by another person from Calcutta, Professor Amal Kumar Rai Chaudhary, working at the Ashutosh College in Kolkata. He studied local properties of flows, and he demonstrated that the local behavior can be decomposed into convergence, rotation, and shear. And these equations are fundamental to studies of singularities where convergence dominates. This is a picture of Professor Rai Chaudhary taken about 20 years ago. So all of this is still theory, but observationally things started hotting up in 1960s because people had started discovering objects which looked like stars, which looked point-like like stars, but they seemed to have a very different kind of a spectrum. It was not known at that time as to how far these are. Martin Schmidt was the first person to decipher the spectrum and realize that the star-like object which is associated with the radio source 3C273, the redshift of that is 0.158, which means it is, if it is expanding with the expansion of the universe, then it is really, really far away. So 3C273, here 3C refers to the third Cambridge catalogue of radio sources, and 273 is the number of corresponding to this source in that catalog. So this was the largest known redshift at that time. I'm sure those of you who are interested in astronomy would have been following news from JWST, where it is now claimed that there are several galaxies with a redshift of more than 10 in the first data that has been released. So the only if the source 3C273 is so far away and still it is so bright, the only viable explanation which was available to theorists was that matter is somehow falling towards a black hole, and then we have to find a way of converting this kinetic energy of the particle, which it gains as it falls into the potential well, into radiation. And the trick which people used was that if the infalling matter has a large angular momentum, then it forms, it goes into an orbit around the central mass, and it gradually sinks in because neighboring orbits, so you have a disk of matter which is going around, but the neighboring orbits are not at the same speed, so there is a little bit of friction, viscosity, because of which matter heats up, and matter heats up to can potentially heat up to very, very high temperatures. And theorists suggested that this hot matter in the vicinity of a black hole could potentially give out this large amount of radiation. So this is something which was being discussed for this very distant source, but theorists also started worrying about nearby sources like Cygnus X1, which was discovered in early 1970s, which is in our own galaxy, but it emits copious amounts of X-ray radiation. And for something to be emitting X-ray radiation, the plasma in the vicinity of that has to be extremely hot. It has to be at a temperature of much more than 1,000,000 Kelvin, 1,000,000 degrees centigrade. And theorists felt that the only way it can happen is if it is falling around a black hole. So for observers, the idea of black holes started hotting up in 1960s and early 1970s. And I think this is pretty much the last or second last picture for theory, which I'm going to show. So Penrose developed the ideas of event horizon, and what he demonstrated was that the light cones, so we know that if we are at some place, and if we draw a one spatial and one time dimension, and then we draw how light will proceed, all the massive particles, since they move slower than the speed of light, will move inside the cone traced out by light. What Penrose was able to show was that the light cone structure itself gets modified, it gets distorted, such that as you go into the horizon or the radius of the black hole, it is not possible for light to come out at all, it can only fall in. Note that this is much stronger than the Newtonian analog. The Newtonian analog was that light cannot escape to infinity. Here it says that light cannot come out of the radius of the black hole at all. So this was shown to be the case for Schwarzschild black holes. And Penrose calls it Eddington-Finkelstein coordinates, although neither Eddington nor Finkelstein published this idea. It was published by Penrose. It is possible that it emerged in Penrose's discussions with Eddington and Finkelstein. So Penrose was able to prove that spherical symmetry is not required, time independence is not required, that once some kind of a horizon forms anywhere, it is inevitable that a singularity will form. And that was his contribution, for which he was awarded the Nobel Prize. Interestingly, at that stage, only one solution for a black hole was known, which is due to Schwarzschild, which was the solution which was given in 1916. And Roy Kerr in 1963 found a solution for a rotating black hole, and this too had trapped surfaces. Yeah. So now we come to observations and observers. Reinhard Genzel, shown here on the right, and Andrea Ghez, UCLA, shown at the bottom left. They got 1/2 of the Nobel Prize 2020 for the discovery of a supermassive compact object at the center of our own galaxy. Before they started their work, so I'm talking about 1980s and early 1990s, people had started collecting spectra, high resolution spectra of centers of nearby galaxies, and they were able to show that the rotational speeds in the very centers of galaxies are very high, and they are so high that it appears that there is a single mass which is dominating motions near centers of galaxies. And by conjecturing that this is because there is a black hole at the center of each galaxy, they were able to infer the masses of these black holes. And interestingly, what they found is that the mass of the black hole in each galaxy is related to how large the bulge for that galaxy is. These two things are very tightly correlated. So this is a figure from a paper published in 2004, and the correlation has proven correlation essentially has been tested many times, and it still seems to be there, and the people have much tighter constraints on this now. So these people wanted to look towards the center of the galaxy. Okay, and so this is Reinhard. He started this project. He wanted to look towards the center of the galaxy, and he had to figure out how to do that. So now if you look at this picture of the our own galaxy taken from the Earth, or an orbit around the Earth. So this is at various wavelengths starting from frequencies starting from 408 megahertz, which corresponds to a wavelength of around 80 centimeters, all the way to gamma rays, which corresponds to a really tiny wavelength of less than 1 angstrom. So at each of these, we can see that there is a lot of emission from the central side part of the galaxy, which is in the center of each of these strips. But we can either see evidence of some gas, or we can see evidence of stars in the outer regions. But it is only in this near infrared that we can see towards the center, and we can see stars at the center. This is because in near infrared, absorption by the intervening gas and dust is least. Doesn't mean that absorption is not there. Intervening gas and dust actually absorbs about 999 parts in 1,000, but situation is much worse in all other wavebands. So Reinhard Genzel decided that he will observe in the near infrared, and he started observing the central part of the galaxy in near infrared on a very regular basis, hoping to discover stars which are orbiting the central black hole in our own galaxy. So notice that this goes back to Michel's ideas, which were given several hundred years earlier. But the main problem is that how do we see stars, individual stars, because when we observe from the Earth, the turbulent atmosphere makes all the images very blurry, and therefore locating stars becomes very hard. So one of the things which they tried is called speckle photography. So what they did was to take a lot of photographs with very short time exposures, so that the blurriness is not there, except that images can be shifted from one image to the next. And then in mid-1990s, they came up with adaptive optics, where you sense the incoming wavefront, figure out how it differs from a plane wavefront, and correct it. And as you correct it, you can get very sharp pictures. How does this work? So basically, you put a lot of, so this is essentially a notional diagram. You can put a lot of individual lenses in the path of the incoming light. So you don't take the main portion of the light, you observe something on one side. If the wavefront was flat, all the foci would be where these dashed lines meet. But because the actual wavefront is perturbed, the foci are shifted. So what you do is you figure out how much are the foci shifted. That allows you to figure out the shape of the wavefront, and then you can introduce appropriate measures to correct this wavefront as you make an image. As bright stars may not be visible, may not be available in the field of view, astronomers have taken to creating artificial stars by using a sodium laser. So this is the first adaptive optics demonstration of adaptive optics in astronomy. This is from 1990. Observations were done in 1989, and you can see that without the correction, you have a strange blur kind of a thing with a central object, whereas when you do the adaptive optics correction, you are able to see two objects where you were seeing only one. So with adaptive optics, people started observing the central part of this our own galaxy on a regular basis, and they started seeing motion of stars at the center. And as they started observing this, they were able to map the orbits of stars near the center. By now, they have a list of hundreds of stars whose orbits have been mapped. And from these orbits, they are basically able to figure out the mass which is contained at the center. So let's see how adaptive optics works. I hope the video works here. Yeah, okay. So this blurry image of the star becomes very, very sharp by using adaptive optics. And then we are even able to pull tricks like block out light from a star so that we can observe in the vicinity of a star and see fainter stars. Okay, so that is how adaptive optics works. This is the galactic center, and these are the stars which are visible over there. And if you look around, you will even be able to find a movie of how these stars are shifting, because by now images taken over the last 30 years are available. So what these people did was to first figure out how does the mass contained within a given radius in our own galaxy change with distance from the center. The units on the x-axis here are kiloparsecs. 1 parsec is about 3.26 light years, and a kiloparsec, of course, is 1000 parsecs. So you can see that as we go towards the center, as we get to 1 kiloparsec, the total mass is a little bit more than a billion times the mass of the sun. Units on the y-axis are logarithmic in terms of mass of the sun. So as they discovered stars going around, as they found out their time period, for example, here you can see between 1992 and 2002, this star has done about 3/4 of its orbit. From there, they can figure out how much mass is contained. And of course, there are many, many stars which have been observed. There are code names for them, S2, S62, X38, and so on. And by combining data from all of these, one can put constraints on how much mass is enclosed. So as we go very, very close near the center, from the star which goes closest to the center, we are able to see that around 4 million times the mass of the sun, that much mass is contained in a region which is just about 10 times the orbit of the Earth. There are other indicators which are able to, which we see, but they don't tell us how much mass is there so well as these stars do. So you can see the error bars are very big. Okay, but using centuries-old ideas from Michel, but modern technology, one is able to put constraints on what is the mass of the black hole at the center of our own galaxy. So the current status is that gravitational redshift has been measured for stars in the vicinity of the central object, and precession of their orbits due to relativistic corrections has been observed, and these verify space-time geometry in the weak field limit. In the last 4 or 5 years, the people have started using interferometry, so they don't just use one telescope, but they use multiple telescopes and use them to do interference of light which is coming in and improve the sensitivity and resolution. This is going to lead to remarkable discoveries in the next decade. So apart from the big black hole at the center of our own galaxy, there also seem to be other black holes which are smaller in mass. So what you are seeing over here, let's focus on the top plot, is the variation of light from a star, faraway star, varying with as a function of time. And all of these data points are taken in 2011. And you can see that the light of this star became very bright for a while and then it became faint. If we focus on the inner part, we can see the shape of rise and fall very nicely. So it turns out that the only explanation that we have for this kind of a brightening and fading away of a distant star is if a very compact object came in between that star and us, and the current best fit is that it's probably a black hole, which is about 7 times more massive than the sun. So we not only have supermassive black holes, which are millions of times the mass of the sun, we also have low and intermediate mass black holes, which are of the order of 10 times the mass of the sun. And this, of course, is now one of the most stunning proofs, the Event Horizon Telescope image of M87, center of M87, where we see this dark shadow in the middle and a bright ring around it. The dark shadow is interpreted as evidence for a black hole. And the way it works is as follows. If I have light coming if I have light coming close to a black hole, then that light ray gets deflected. If it comes closer, it gets deflected even more. If I try to send it closer, it will either fall in or it will do 1, 1.5 or 2, 3 loops around the black hole and then go away, go out again. So if this happens, then it is clear that for a distant observer, we are not going to get any light ray coming from the center of the black hole. We will only get it from the outer part. So this is the photon sphere, which we talked about early on. So the radius of the photon sphere for a non-rotating black hole is 1.5 times the radius of the black hole. So by looking at the size of this ring and mapping it to the photon sphere, we are able to estimate the mass of the black hole in M82. Similar observations have been done for the black hole at the center of our own galaxy as well. So M82, the black hole is more than 1 billion times more massive than the sun. Black hole at the center of our own galaxy is several million times more massive than the sun. But the black hole at the center of M82 is being fed, material is falling into it, and it has a very steady accretion disk, whereas the black hole at the center of our own galaxy is not getting a regular supply of gas, and hence it was fairly difficult to image that. So to recap, we have theoretical reasons for believing that black holes can form. We have observational reasons to convince ourselves that there are observations, for example, at the center of our own galaxy, where there seems to be about 4 million times the mass of the sun amount of mass in a very, very compact space, which is comparable with the radius of the sun, the Earth's orbit around the sun. Therefore, and because we are unable to think of anything other than a black hole which satisfies these requirements, we pretty much believe that a black hole is sitting over there. Of course, a convincing proof would be if we are able to shrink the distance constraint further by a factor of 20 or so. So that will make it ironclad, because then there will be no possible theoretical model which can give us an object, non-black hole object of that size. So the Nobel Prize 2020 recognized the theoretical advancements and observational work that established black holes as astrophysical objects. The citation shies away from stating that Genzel and Guess have established the presence of a black hole. Roy Kerr and the EHT team perhaps have a stronger claim on that count, and I hope that in coming years they will be rewarded by a Nobel Prize. And perhaps that will be the last black hole related Nobel Prize. Thank you. I'll stop here.
Thank you so much, Professor Bagla, for sharing such a comparative study and giving so detailed information about the topic we have discussed. So now the session is open for the question and answer and your doubt. We can take some of them during the session. Anything you would like to ask? Yes, we have one question. I'm just pointing it on the screen. Vaibhav Kataria. Hi, I'm an amateur, so pardon if this sounds silly. Read about Hawking's radiation, but is there an actual observation where a black hole disappeared?
Yeah. So the Hawking radiation basically talks about radiation coming from the vicinity of a black hole. It's a astroparticle calculation. And in the process, indeed, black hole is supposed to lose some mass. Interestingly, the amount of mass that it loses, as the rate at which it loses mass, is comparatively high for low mass black holes and very, very small for high mass black holes. So as a result, high mass black holes will take enormous amount of time to disappear. And of course, you have to make sure that nothing falls in that period, because then they will gain some mass again. Whereas low mass black holes, which are much, much smaller than 1 gram, they could be evaporating around now if they formed in the early universe. So there have been conjectures on formation of very tiny black holes, and relating Hawking radiation from such evaporating black holes with some astrophysical phenomena, but unfortunately none of those has worked in a convincing manner.
So hope, Vaibhav, you got your clarification. Thank you for asking the question. Anyone would like to ask can drop in the chat box. We'll be highlighting those questions so that Sir can take those. So again, I would like to, meanwhile, anyone would like to ask and drop in the chat box. This video is available on the Planetarium YouTube channel. In case anyone would like to refer later, feel free to do that. Yes, other thing, like you said about a walking black hole.
Wandering black hole, yeah. Yeah, so what is the question? Wandering black hole in the sense that it is moving in somewhere in our galaxy. We don't know where it is. We happen to see its effect on a background star when it passed between that star and us. So we can say a little bit about how far it could be, or how fast it is moving, or how massive it is. But because we have not seen it, these constraints are somewhat tentative.
So I think he asked in like in two questions. So I'm just reading those. How do you differentiate between? And the next question is black hole disappearing and moving. So I think this
a
was
disappearing black hole will have to emit a lot of energy. Okay, so evaporating black hole which disappears will have to emit enormous amounts of energy, and we will see that. We will see that if not in optical light, then in gamma rays or something. Whereas a moving black hole is just moving along. It just passed in front of an object and then made it appear bright for a while, and then it disappeared as far as we are concerned, until it appears in front of another star. So far we have only one such observation, although there are observatories. So this particular observation was taken by a Polish group. They have a program called OGLE, and they have been observing 1 million stars on a weekly basis for the last 25 years. Okay, so it requires a lot of hard work to track all of these stars, make sure that you can monitor brightness to a very, very precise level. And that is how they have discovered one black hole. hopefully in future such programs will be expanded to cover more stars, and they will be able to discover more black holes of this kind. But a black hole which is just there is very, very different from a black hole which is evaporating and disappearing.
So with this we have M. Kumar. Sir, is there white holes?
No, not that we know of. There is no proper theoretical construct of a white hole.
Shiva Mukherjee, how many black hole collision have we detected till now?
Okay, so black hole mergers, they are not just collisions, they are mergers, two black holes coming and merging with each other to form a bigger black hole. Around 50 of these have been observed via the gravitational waves which they emit. So observatories like LIGO and Virgo have made these observations. Close to 50 such things have been observed. First discovery was in 2015. So it's been 7 years. In 7 years, they have detected around 50. But now they are starting. So every time they restart the instrument, it has a higher sensitivity because they keep upgrading it. And we hope that in the next cycle, they will detect a couple of hundred such events in 1 year.
Vaibhav, so far what I have read about black holes, we do not have any certain data about them. So for a moving black hole, suppose there are few 50 black holes as such. And also he's very
Uh,
in connection. I think Vaibhav, this is in connection. How sure are we that they just wander, and how can we predict where it would be when there are
right.
theories that can bend gravity and time?
Right. So what people do is they assume they don't have a theoretical reason for theoretical model for telling them how many black holes are there. So they just say that suppose I have this many black holes in the galaxy of this much mass, then what will be the observable effect on background stars? And then by comparing with observations, we can rule out some scenarios. And we cannot rule out some because some scenarios may predict one such event in 50 years. We have seen one and we will be happy. Whereas another scenario which predicts 1 in 20 years would be perfectly valid. We just have to wait another 10 years or so to see the next one. So uh, theoretically, people just scan the possible numbers or number densities of black holes and masses of black holes and see how they can be constrained through observations which are already available. The next step which they take is for things which they cannot rule out, they make predictions of what might be seen so that 5 years or 10 years down the line, we can revise the constraints using updated observations. So the number of wandering black holes cannot be very high.
So I think Vaibhav, you got the clarification on your query. Also, what can you explain? What is the true nature of the event horizon? Does it correspond with hologram 2D information theory, the firewall theory, or it is a silent barrier?
Okay, at a classical level, it is a one-way membrane. At a quantum mechanics level, quantum field theory level, there are different approaches to it, and that is where the hologram or holographic models and information theoretical models come into play. Those models are still being developed, and therefore, I don't think there is anything very definitive which we can say right now. But the classical model of black holes, they are essentially one-way membranes.
So I
You
think
can go in, you
in
cannot
the
come out.
same connection, he is mentioning: is there a way to send a probe into a black hole in the future? If yes, what must we do to ensure it reaching the black hole and transversing the event horizon?
Or we can send a probe. That is not a problem, except that we will not know what happened to it. The main difficulty with such probes is that the tidal forces near black holes can be strong, so they can tear apart a probe which may be trying to fall in. So the trick then is to choose a very large, heavy, high mass black hole, because for a high mass black hole, the tidal forces are not very strong at the event horizon, and therefore an object can easily go in a single piece without being torn apart. The only problem is that the probe will go in, but probe will not be able to send any information out.
Hope Shivam, you also got your clarification on your doubts. I think with this we'll wrap today's session, because black hole is one of the topic in which always excites the arouse so much questions amongst the amateur as well as the space enthusiasts. So probably we'll definitely gonna plan it in future as well, so that more clarification we could get it. And hopefully, sir, in the coming time, now the situation is better in terms of COVID concerns. So we love to host you at the planetarium so that we can have one-to-one interaction. And
Absolutely, I would
all
love to
the
do that.
Delhi NCR students of school, college, and amateur can have that time with you to ask impersonal questions related to the topic we're gonna host in the planetarium. So with that,
Absolutely.
yeah. So with that, thank you everyone. Thank you for giving your time and coming online and attending this session. Thank you, Professor Bagla, for accepting Planetarium's invitation. And we love to collaborate in future as well. Thank you so much for your time, sir.
Thank you. Bye-bye.
Thank you everyone. Do take care. Thank you.